Okay, I wanted to just kind of share some final thoughts, maybe try to pull the semester together a little bit as far as seeing a little bit of a big picture here rather than all the little pieces that we've been looking at. So, anyway, some final thoughts. First of all, I'd like for you to kind of sit back and reflect a little bit. Try to see this a little more completely from start to end. Here's what we've been trying to accomplish in the semester. We've been trying to end up to a point where we can understand, analyze, then design a controller for a system. And we've been looking at it very generically so that we can apply it to any kind of application that we want. But the general process that we've been following is to first model the system. And if we can model the system even reasonably, we probably can get an adequate controller for it. One of the great things, the magic about control systems, especially closed loop controls, is closing the loop will do a lot to compensate for a bad model. Even if we get it close, and we can design a controller that is reasonable for that closed system, then when we close the loop on the real system, it will function, usually will function at an adequate level. So most of the time, a first or second order system should be adequate to describe the systems for a typical application. Nothing exotic, but just a run-of-the-mill kind of stuff. You can model as a first or second order system depending on the application, and that probably will get you close enough to get your controller to understand what the system's doing, enough to understand what you need in the way of a controller, and get your controller close enough that you can work with it. So model the system, and then we're going to be doing the analysis of it. We looked at two broad methods, one the root locus and then the frequency response, where we're looking at the roots and the time domain response in the root locus, and the frequency domain, we're feeding it a sine wave and seeing what the response is. And hopefully at this point, as you look at them all together, say in like a SISO tool, they each have their advantages, but we can use them all together to understand what the system is doing. And that's our first goal as controllers. Control engineers, is to understand what the system is doing. If we don't understand what the system is doing, then we don't know what to do to control it. And so if we can analyze it, we see where what it's doing in its natural state, then we can start thinking about what it is, how we have to modify it. So from there, we need to figure out what it is that we want to do with the system. How fast does it have to go in far as response? What is the overshoot? What is a steady state error? Knowing our parameters then gives us some place to shoot when we start designing our controller. So start thinking about designing our controllers. Now, I'm going to talk about this a little bit more, but our controller can be anything, okay? Anything tangible. I mean, especially in the era of microcontrollers and code that describes the controller, we can put whatever gain and as many zeros or as many poles or whatever we need in there. We can design a custom controller for our specific application. Okay, and we can do nonlinearity. We can clip it. We can do all kinds of interesting stuff to our controller. That being said, for most of the work that a typical engineer runs across, you probably are going to be thinking about a PID controller. Okay, this is a off-the-shelf standard controller everybody understands and is widely available. So and it works. It works in most cases. Some version of a PID, a proportional or PI, PD, or a PID, works in many applications. And so we we tend to gravitate towards a PID controller for our controller. Now, remember, when you do that, in your analysis, you're going to come up with a controller in the ZPK form, zeros, poles, and gains, and which is going to have to be then converted to KP, KI, or KD and KD, so to put into your controller for a PID. Once we have the controller designed, or think what we want to do with it, then comes down to the implementation. And the implementation, in many cases, is fairly simple. You're talking about a sensor. You've got to measure what you're going to control. If you can't measure it, you can't control it. And so we're going to measure it and figure out what it is. We're going to figure out, I need some sort of actuator. You're going to need to be able to manipulate the system, higher, lower, up, down, right, left, whatever. You're going to need to be able to move the system with your controller. So sometimes that's you can get right into the heart of it and connect your controller right to the heart of your system and make it go, or sometimes it has to be a secondary system that moves your system around. So, but you got to have some sort of actuator, and then the controller itself. And so this may take the form of a microcontroller, maybe some sort of off-the-shelf PID, or it may be a PC. It can come in all different kinds of forms. What we tend to look for is, or tend to look at these days, is microcontrollers, and in industrial settings, off-the-shelf PIDs, and in large-scale applications, these are all the controllers may be routed to a single computer bank in a controlled environment that is controlling the individual components. So, the implementation is actually fairly straightforward. You got a sensor, actuator, and some sort of controller on there. Then we're going to test it. Once we get it, we're going to test it, and then we're probably going to tune it. And I didn't put tuning on there, but it probably is not going to react exactly like your analysis shows. And so then you're going to have some tuning associated with it, tweaking it just a little bit to see if you can improve the performance of the system. Now, the other route is a little more hands-on, and you skip the modeling and you skip the analysis, and you go directly to implementation of a say a PID controller, and you tune that PID controller for the application. Very, very common type way to use or to implement this stuff is to, especially if it's a system type that you're familiar with. If you work in boilers and you're trying to maintain the pressure in a boiler, you will have implemented controllers on boilers, and you don't need to analyze them. You understand how they work, and so you know what kind of controller and how you're going to set the controller basically. And so you implement the controller and you tweak it up, tune it for the application, and you move on to the next problem. And so test and tuning is a big part of what a control engineer would do. So that's an overview of what you would be doing as a control engineer in many kind of applications. And you guys will run across this. You will see control applications, and so be aware of what's happening with them and how you can use them and work with them. Going back to the controller, I wanted to hit just again on a little bit of controllers. Now, a microcontroller, like we might see here, like an Arduino. Arduino is a common and very popular microcontroller these days. It's not particularly hardened or robust, but it can do a really good job in a lot of things. If you're going to do this for an industrial application, you're probably going to be doing some sort of something a little bit more robust, a little hardened. But but a single board controller, microcontroller, is probably something you're going to be looking at, and you would be implementing something like this kind of code. This is a simple implementation of a PID code. I've showed you this before. You would implement that on the Arduino or a single board microcontroller and hook it up, input and output, and turn it loose and let it go, and tune it along the way if you want to. So that would be one approach to the system. Another one that in application or implementation of this would be a PID controller. Now these can be purchased directly off the shelf. Okay, here's some examples of PID controllers that I pulled out of catalogs, and you purchase a PID controller, and you hook your sensor into it, you hook your output into it, and it has the parameters already set up. So you set the gains, and it monitors the temperature, the pressure, whatever, and it controls it. And so this is a very easy way to implement a PID controller, and these would be used in like an industrial setting where you want something robust and hardened for the environment. Now, another thing that I wanted to mention to you is PLCs. Okay, now if you go out and look for a control engineer's job, or if you come across a control engineer's job, there's a pretty good chance that what they're talking about is an engineer that understands how to implement and program a PLC. Okay, and PLC is a programmable logic controller. It is a device that it does a form of control. We tend to look down on it a little bit because it's a pretty low level, or it used to be a pretty low level kind of thing. It was a bunch of switches and timers, and so you would run this thing for so long, and then it would switch off, and another thing would switch on, and it would run that for so long, and if this happened, then that would switch this off and switch that on, and it was a logical controller. So depending on what was happening with the switch system, it would switch this off or switch that on. Common application that I always comes to mind is like a washing machine in your house. You throw your clothes in there, you set it on a cycle, and that cycle, the first thing it does is it opens the water valve and fills the tub up with water, and it probably has two valves, one for hot and one for cold. So depending on what the cycle is, it'll open the hot, open the cold, or open both of them. And then once that's open or done, those switch off and those valves close, and then the agitator starts. And so the agitator motor starts and agitates, and maybe dumps some soap in or something like that. Opens a valve that dumps soap in, and then once that's done, then it drains the water. Opens a valve that drains the water, and then it spins cycles, so it spins the drum. And so it's a series of acts or commands, and that's what a PLC does. Is you program it in a language called ladder logic. Now, the interesting part about this is these have evolved over the years, and now they're solid state. They actually have a microcontroller in them, and some of the functions can be programmed with a PID controller. So if you had something like a PLC controlling say a dryer, and you wanted to keep the dryer at a constant temperature, you could implement a PID controller within the PLC for the heating of that drying element or drying unit. And so you can do these more sophisticated control applications within a PLC these days. Learning how to do a PLC is a great thing. And a lot of applications to those, especially in industrial settings. These are widely used for like industrial conveying lines where you have a sequence of events happening. So a PLC would handle those kinds of things. So anyway, just a short overview, get you thinking about and trying to integrate all this that we've learned over the semester. I hope that you've enjoyed the class, and I hope that you all become great control engineers.